Like many great stories, the story of Git LFS actually begins in Paris. It was the 8th of April 2015, and a bunch of engineers were sitting around at the annual Git Contributors Summit that happens the day before the Git Merge conference to talk about how everyone's going to develop Git for the next 12 months. Now, at this particular Git Contributors Summit last year, a couple of Atlassians were talking to a couple of GitHubbers. So I'm an engineer at Atlassian, and we maintain Bitbucket. And GitHub and Bitbucket are traditionally pretty staunch competitors when it comes to Git hosting. And the conversation between Nick Paolucci and Rick Olson, Nick's from Atlassian and Rick is from GitHub, went something like this. Nick said, hey, at Atlassian, we've been working on this new extension to Git to solve the problem that Git has with storing and tracking large binary files. So we've built this new extension in the Go programming language, and we're planning on announcing it at our track session during Git Merge tomorrow at the conference. And Rick from GitHub said, it's kind of interesting you say that, Nick, because at GitHub we've also been working on a solution to solve the problem that Git has with storing large binary content. We've also built a new extension to Git in Go, and we're planning on announcing it at our track session at Git Merge tomorrow, directly before yours. And Nick from Atlassian went, what? That's a picture of James Watt, by the way. And Rick went, totes, it seems like we've both built tools to solve exactly the same problem. What do you call your extension? And this is where it gets really weird. Nick said, well, we call ours Git Lob, after long objects like you might find in a database. And Rick said, well, that's kind of funny because we've also picked a three-letter acronym starting with L. Ours is called Git LFS, for large file storage. And after a bit of back and forth between Nick and Rick, and eventually Atlassian and GitHub, we at Atlassian decided to open source and mothball the Git Lob project. You can actually see it up on the Atlassian organization on GitHub, if you like, and start porting over some of the features that we built into the Git LFS project. Now, we did this for a couple of reasons. The primary one is that we didn't want to fragment the community. One of the nice things about Git and all of the various Git hosting providers is that Git is a relatively portable data format. Other than a little bit of project metadata, it's pretty easy to migrate from one provider to another. So we didn't want to have two different solutions for solving exactly the same problem of storing large binary content. And the other reason we decided to join forces and start collaborating on the same project is that although they were developed completely independently without knowledge of each other, Git LFS and Git Lob are both actually designed in a very, very similar way. They both use the same set of extensions that Git uses for extending itself, and they were both built in Go. So it was relatively straightforward for us to port all of the work we'd done on Lob over to LFS. So that's why I'm here today to talk about tracking huge files in your repositories with Git LFS. Now, I've done quite a lot of Git evangelism in the past, talking about different workflows and the power of Git's core and all of its awesome features like rebasing. But the reason I'm really excited about LFS is not just because it allows me to track my large content, but it means that every software team in the world can now migrate over and start using Git. Traditionally, it's been really hard for certain types of developers to use Git because of its limitations with tracking large content. If you were a game designer with large binary assets like model objects or textures or video files, it's really hard to version that stuff alongside your source code inside a game, even though that would be quite convenient. Similarly, if you're a researcher working with huge data sets that you need to version alongside the scripts that you're building for your research, or training data for neural networks, storing that stuff in a Git repository gets cumbersome over time because of the fact that Git is a distributed version control system where you have to copy around the entire repository history when you want to work with it. Also, web developers with rich media, it would be really cool if you could version that alongside your site's actual code, or QA engineers or other developers who need to store things like database snapshots for their functional tests can start actually versioning those huge artifacts directly in their code base where it makes sense. So all of these teams and developers who are stuck on centralized version control systems like CVS or Perforce or Subversion can now switch over to distributed version control because of Git LFS. And that's why I'm really excited about the project. So today I'm going to talk a little bit about why Git has such a hard time with binary content in the first place and sort of explain where the genesis of Git LFS came from. Then I'll talk a little bit about how LFS solves this problem, and we'll peek under the hood at some of the technology that LFS uses. Then I'll give you some tips for converting your existing repositories over to use Git LFS if you're already tracking binary content inside them. And finally, I'll give you some tips for using LFS in a team workflow. So to understand why Git has such a hard time tracking binary content, you need to know a little bit about the way that Git actually tracks your repository contents. So Git has a huge collection of different types of objects that it stores with your repository. Kind of the one which you're probably the most familiar with is commits, which are revisions or snapshots of your code base over time. And these commit objects are actually related to each other via ancestry. Specifically, each commit contains a reference to its immediate parent, or parents in the case of a merge commit. Now this data structure is actually known as a DAG, or a directed acyclic graph, because each commit has references to other objects within the data structure, making it directed, and because the data structure itself is immutable, you can only ever add new objects to it, it's acyclic. You can never end up with a cycle inside your set of commits and edges. Now, if we throw in a couple of refs, more commonly known as branches or tags in Git parlance, you start getting a bit of a better picture as to what the Git data model looks like. Now, to understand why Git has a hard time with binary content, we need to look a little bit deeper at the structure of these commit objects. So there's a command that Git ships with called cat file, which you can use for inspecting objects inside your Git data store. Now, if you pass it a commit ID and use the -p flag, which stands for pretty, it'll show you the actual content of one of these objects. Now, commits are actually pretty lightweight. As you can see, it's got a reference to the commit's parent in one field. It also has a reference to a tree object, which is roughly equivalent to a directory on a file system, and that's how Git actually structures and organizes the contents of your repository. And then you have a little bit of committer metadata, including the person who created the commit and the person who authored the code. Now these will usually be the same person depending on your workflow. In the Linux kernel, it's not necessarily, because different people are going to be authoring code and committing it due to its use of patch sets. And then you also have a little bit of committer metadata as well. Now these hexadecimal IDs that you see all over the place in Git are SHA-1 hashes of the object's contents. So Git is actually what's known as a content addressable file system, because each object is ID'd by a SHA-1 hash of its contents, which has a couple of really useful properties. One of them is it's very easy to determine if two objects are duplicated because you have this SHA-1 hash. So Git's very, very good at reusing the same object if it doesn't change between commits. We'll see why this is important in just a second. Now, if we take the SHA-1 hash of that tree object and pass it to our cat file command, we can actually inspect the structure of one of these trees. And you can see that a tree looks a lot like a directory on a file system. You have some file modes describing the mode of each one of these objects sitting under the tree. You have the type of those objects, which is always going to be either a blob, which is actually the contents of a file in your repository at the point in time when that commit was created, or another tree, which is basically a nested directory inside your repository. So this top-level tree object referred to by a commit is actually analogous to the top-level directory of your repository at that point in time. So you can actually recurse down through this top-level tree, through all of its subtrees and blobs, and get what looks like the full layout of your repository. So if you wanted to, you could actually go down and inspect all of the contents of your repo using this command, although that would be a very slow way to get a file tree of your repo. Now, if we throw back in a ref, so this could be, for example, be our master branch, we have a pretty complete look at what the Git data model is. So it's actually relatively simple. To be honest, if you're sort of new to Git, or you're still kind of struggling to understand what all of those different crazy commands like rebasing and merging and cherry picking do, coming to grips with how the Git data model works is actually a pretty good way to learn about that. After you've sort of got this mastered, you start thinking of all those commands as operations on a DAG rather than just kind of blindly typing them in and hoping that they work. Now, the reason Git has such a hard time with binary content and large files in general is that Git creates a new one of these tree objects every time you create a commit. So you end up with a huge number of these trees and blobs sitting around in your repo. Now, as I mentioned, Git is content addressable, so it's very good at reusing blobs that don't change. So it only creates new blobs for files that actually change in between commits, but that still means you end up with a huge number of these blobs. Now, Git does eventually delta, it actually stores all of these blobs zlib compressed, and it does do some delta encoding eventually, but delta encoding doesn't work very well for a lot of binary file types because they're already compressed. So it's actually quite hard for Git to store these efficiently. So to understand why we have such a hard time with large binary content, let's take a really trivial example where we have a repository that contains a single file, a high-resolution photo of an elephant. Say it weighs in at like 50 megabytes. Now if I come in and change the hue of that elephant to pink and commit it back to my repository, at first it's going to basically double the size of my repo because Git has no way of semantically storing that I've just changed the hue of that elephant to pink. And so on and so forth. Every time I make a modification, it's going to create a new blob under the hood, and my repository size is going to bloat and bloat and bloat. Now this isn't some defect with Git. Subversion and Perforce and CVS and all of those centralized version control systems have exactly the same problem. But the problem with Git is that it's a distributed version control system. So after I've made all of these modifications, I'm going to push them back up to my Git hosting server, and then every single person on my team who wants to work with my codebase is going to have to retrieve every version of that file. Now with a centralized version control system, they don't copy the whole repository around. They just pull down the latest commit or snapshot of your code. So unfortunately, Git's awesome power of distributed version control is actually kind of a weakness when it comes to this large file content. Now Git LFS is a solution to this problem that, as I mentioned, is a joint project between Atlassian and GitHub. Now the key way that Git LFS works is rather than storing all of this large content directly inside your repository, instead you store these lightweight pointer files that refer to these large objects that are actually stored in separate storage. So when a developer does a git push on a Git LFS enabled repository, your large content gets transferred to a separate parallel LFS store, and your git dag gets transferred to your Git host as normal, with each of these pointer files weighing in at only a few bytes instead of megabytes or gigabytes depending on the binary content that you're working with. And similarly, when a developer does a git pull, their git dag comes down as normal, but then Git LFS only inflates or replaces these pointer files for the content that's sitting at the tip of the branch that you just checked out. So all of those interstitial versions of that file that are sitting around in your history stay in the LFS store until you actually need to go back and check out one of those commits. Now if we use our handy cat file command again, we can inspect what one of these pointer files actually look like, and they are ridiculously tiny. It's literally 3 fields. There's a version number, or a version URI, which is kind of the new fancy way of doing numbers. Then there's an object ID, which is a SHA-256 hash of that object's contents. So Git LFS is also content addressable. It does use SHA-256 instead of SHA-1 though, which is what Git uses. A couple of reasons for that. The first is that SHA-1 is quite an old standard these days. So Git is almost 11 years old at this point, and SHA-1 has been shown to be theoretically a little weaker than its original design constraints. So SHA-256 is a more modern standard. And because of this, some of the backing stores you can actually use for LFS, for example S3, has built-in support for SHA-256 verification of these objects. So using SHA-256 for this is kind of a pragmatic choice because it means we can auto-validate objects in some of these backing stores. And then also we have the size of that object in bytes encoded as the last field in that pointer. Now, one of the reasons that there have actually been other attempts to solve the large file problem in Git before. There's a tool called Git Annex, one called Git Media, one called Git Fat, Git Big Files. But the reason Git LFS, I think, is becoming way more successful than those previous projects is a couple of reasons. The first is it's written in Go, and so it's available on basically every platform that Git is available on. And two, it maps very, very cleanly onto your existing Git workflows. So once you've got Git LFS initialized in a repo, you basically can use your existing workflow as normal. You don't have to have any special knowledge of how LFS works or run any special commands to transfer this content to the server and back. LFS handles all of that using Git's extension system. So installing Git LFS is very simple. Use your favorite package manager. You can use Brew or Yum or whatever you like, or you can compile it from source and install it locally. Once you have it on your path, you can simply run git LFS install to get it initialized. And all Git LFS install does is add this new entry to your global Git configuration, which is setting up a thing called a filter. So Git has this filtering system that allows you to tell Git how to handle certain types of files that it comes across in your repository. It actually intercepts different Git command invocations based on that file type and allows you to run some arbitrary code. So it's actually setting up a thing called a clean filter and a smudge filter to hand off the contents of these files that it finds in your repo to the Git LFS clean command and the Git LFS smudge command. We'll look at how those work in just a second. Once you've got Git LFS installed globally, you can start running the Git LFS track command on a particular repository to bind certain file patterns to that LFS filter. So when you run Git LFS track with a particular pattern, it adds a new entry into this Git attributes file that sits at the root of your repository. Or you can actually nest them in subdirectories as well. But by default, just putting it in the root is the easiest thing you can do. So what this Git attributes file does is tell Git how to handle certain types of files. It's actually mapping the filter operation. So it basically says, hey, if you come across one of these files when you're performing a git add or a git checkout, hand it off to the LFS filter instead. It also binds the LFS filter to diff operations and merge operations. So we'll use those same binaries to compute diffs or perform merges. And then finally, that dash text at the end means don't try to compute textual diffs for files of this type, because that doesn't work very well for binary files. Now, how the clean filter works is it intercepts the developer invoking the git add command. So when you run git add and pass a collection of file paths to it, it traditionally just basically adds those to the git staging area or the git index, ready to be committed. But if it comes across one that's been mapped to an LFS filter using Git LFS track, it hands it off to this LFS clean command. Now what LFS clean does is it takes a SHA-256 hash of that object's contents, so in this case, for example, an MP4 video file, and then it writes out the contents of that object into a special directory sitting underneath your Git repository store in .git/lfs/objects. Now Git itself knows nothing about this directory. It's just purely a little object cache for LFS to store content prior to you pushing it to the server. Then it takes that SHA-256 hash and writes it out into one of those pointer files that we just looked at. And then that pointer file is what actually gets added to your Git objects directory, where Git stores all of the other data about your repository. So instead of adding megabytes or gigabytes to your repo, you're only increasing the size by a few bytes from that pointer. Now the Git smudge command does the opposite. When you check out a commit or check out an individual file, if it comes across one of these pointer files, it takes that SHA-256 hash and tries to look it up in that Git LFS objects cache that you have locally. Now at this point, if it doesn't find it, it'll actually read through to your backing LFS store wherever your large file content is being kept. And then it'll write that into the local cache and actually write it out into your work tree. So as a developer, you only actually ever see these large files. You'll never see these pointer files sitting around on disk because the LFS clean and smudge filters will swap them in and out of your work tree automatically. So to be honest, I've kind of been wasting your time for the last 10 minutes telling you about this pointer file format because in practice, you'll never actually see them while you're using Git LFS. Now I want to talk a little bit about how Git LFS actually transfers these large files to and from the server, because it's kind of one of the reasons why LFS is becoming so successful. The way that it transfers files to the server is using a thing called Git hook. Has anyone worked with Git hooks before? Anyone? Yeah, a few people? Cool. So Git has this extension system called hooks, which is orthogonal to the filtering system that we looked at before, but it's another way of intercepting certain Git commands. At Atlassian, we use the prepare commit message hook to precede commit messages with Jira issue keys, for example. So you can actually pull the issue key out of your branch name and insert it into your commit message automatically. You can also use hooks to intercept like the commit command. So if you have some really fast unit tests that you want to run locally, you can set up a pre-commit hook to actually run those tests before a commit is created. Which has a really nice property in that you know that every commit in your repository is passing the tests before it even gets created, which is kind of a nice invariant to have. Now the hook that Git LFS uses is a thing called a pre-push hook. Somewhat predictably, this intercepts the push command and allows you to take some action before that occurs. So when you run a git push on an LFS-enabled repository, when you've created some large file content, you'll see some output from Git LFS saying that it's transferring these files to the server. And similarly, when you run a git pull, you'll see some output from that smudge filter as it's coming across those pointer files. It's just replacing them by reading through to the backing LFS store and downloading them for you. So this is really nice. You don't have to run any special commands. You just run git push and git pull, and it does all the transferring for you. And the other thing you'll notice is that there's no prompt for authentication. So Git LFS actually piggybacks your existing authentication with your Git provider in a really neat way. So I might actually go into how that works just here. So for an HTTP repository, a repository served over HTTP as opposed to like SSH or the Git native protocol, Git LFS already has an HTTP URL location for your repository. So what LFS does is it tacks on a special path to the end of your repo address, and it uses this to communicate with a Git LFS aware provider like Bitbucket, and sends a JSON structure saying, hey, there's this LFS object that I've found in a pointer file. I need to know where to download this content from. Then the LFS aware provider sends back a similar JSON structure saying, hey, this object exists and you can download it at this location over here. But the way that it handles authentication is kind of neat, because this JSON structure is kind of a piece of hypermedia, really. So it actually, instead of just giving you the location of the object, it also gives you the headers that you need to apply to the request in order to download it. So for example, in Bitbucket, we just use a JWT token because your large content is actually stored in the Bitbucket server as well. So we can just sign that with your username and then go, okay, when I receive this header later on, I know that it's this user attempting to download it. But this application of hypermedia is really flexible as well, because if I wanted to use S3 or something, we could put AWS credentials and a basic authorization header here instead, or we could use OAuth2 bearer tokens, or really any kind of authentication scheme that we can dream up, and it will just kind of work. So it gives LFS implementers a lot of flexibility in where they actually want to store their data. So that, in a nutshell, is how Git LFS works. Now I want to talk a little bit about how you can convert your existing repositories over to use Git LFS if you're already storing large binaries inside them. Now I mentioned that Git LFS track command before. That works really well if you've just started a new repository, but it doesn't work very well if you've already got some large objects littering around in your repository history. Because if we run Git LFS track, it will convert those large files to pointers the next time we create a commit. But that's not going to do anything about those large objects sitting in our history. So we need to go back and do something with those. Now, if you're familiar with Git, you might immediately reach for the filter branch command, which is kind of the Swiss Army knife of rewriting repository history. Has anyone used filter branch before? No? Okay. Oh yeah, a couple people? Yeah, so it is very cool and extremely powerful, but it is pretty arcane to use. Like, I don't know what any of this means unless you sort of go through and kind of step through and go, oh, okay. What this command is actually doing is deleting every file that it comes across that's named big_video.mp4. Now this would work in terms of like drastically reducing the size of our repository, but it would also kind of suck because it means that that history is gone. And we probably added these files to our repository in order to be able to go back and check them out at some point. So instead, what you want to do is actually replace those large files in your history with those LFS pointers. Now you can use filter branch for this, but it gets extremely hairy. This is a filter branch command dreamed up by Andy Neff, one of the core Git LFS developers, and it will go back and run the LFS track command on every single commit in your history. Now this will work, but it will be extremely slow. And also kind of scary. Like if you mistype something, it's going to do something crazy to your repository history that potentially is going to be difficult to recover from. So these days, I recommend instead of doing this, you can use a tool called the BFG repo cleaner instead, which has first-class support for Git LFS rewriting. Now the repo cleaner is has anyone used the BFG before? I mean the repo cleaner, not the gun. No? Okay. So the BFG repo cleaner has been around for quite a while. It was actually developed by Roberto Tiley from The Guardian. He had a bit of a problem where he discovered that someone had committed some sensitive credentials to a repository quite a long time ago, and he needed to go back and remove every instance of this particular file from history. So rather than using filter branch, instead he built a new tool in Scala on top of the JGit project, which is a complete reimplementation of Git in Java. And initially it was built just to kill history. So you could delete an entire file from every single commit in your history. You could delete an entire directory, or you could even go in and replace individual tokens within files. So that's really handy if you've got a properties file or something like that with a sensitive credential sitting somewhere inside it, where the rest of the file is still kind of important, but you just want to go back and replace that with asterisks or something. You can use the repo cleaner to do that. The other nice thing about the repo cleaner is it's very, very fast compared to filter branch. Now, filter branch by default will actually walk through and process every object inside your DAG. And that means that often it can process the same trees and blobs over and over again throughout your history. The repo cleaner memoizes trees and blobs that it's already processed and will skip over them after it's rewritten them the first time. And they've actually got this spreadsheet attached to the BFG project on GitHub where it shows equivalent filter branch and BFG commands running on different various open source projects and then the time it takes. And it sort of varies between 10 and 720 times faster depending on the shape of the repository. And finally, since version 1.12.5 of the BFG, it has built-in support for Git LFS. So instead of this fairly awesome but fairly gnarly filter branch command, you can just run, we can install the BFG, which again is built in Java, so very, very portable. You can just run BFG convert to Git LFS, pass it a set of patterns, and it'll convert your repository for you. Now there is still one slightly arcane command you have to add in here, and that's no blob protection. What this means is, by default, the BFG doesn't rewrite your tip commit, so it kind of assumes that you've gotten your repository into a good state before you run the BFG. However, with LFS, you probably actually want to rewrite the tip commit or the head of your main repository branch as well. So you can pass the no blob protection flag to do that. So that's how you rewrite your repository history to use LFS. And that works pretty well if you've got a small repository or you're fairly intimately aware of its history. But in some cases, if you've got a large project or a project with a very deep history, you may not know where all of your large objects are sitting. So there's another tool, or rather a set of scripts that you can use called RepoFactor, which was written by a gentleman from Bloomberg called Charles Bailey. He actually presented this at Git Merge earlier this year. Now RepoFactor is a set of scripts for rewriting your repository history, or more accurately, deleting your repository history. But it also has some scripts for identifying large objects sitting in your repo history. So you can use a combination of this and the BFG to convert your repo over to LFS. Now, if you look at the RepoFactor repository, it's not really an application, it's more just a set of scripts. So kind of the easiest way to use it is by piping a set of these together. The first one you're going to want to run is generate larger than. And basically what this does is it shows you a set of objects larger than the integer threshold that you pass to it. So for example, if we want to find objects larger than 50k, we pass it 50,000 and it gives us this kind of arcane output. And what this output is saying is that there's these blobs with these SHA-1 hashes that were found that are this size on disk. But then it also gives us the average blob size of a thing called a delta chain. So it actually goes and finds a set of blobs that are related to a particular file that's changed over time, and then it finds out the average size of each one of those blobs. So what you kind of want to look at here is rather than just the size on disk, you want to see how that size is kind of averaged out over time. And if that size is also large, then it means it doesn't compress very well. And that means that you should probably consider that as a candidate for LFS. So once you've got this set of objects, you can pipe it to the add file info command, and it actually runs the bash file command. Oops, sorry, skip forward a little bit there. It adds the bash file command to its process and actually outputs a little bit of information about what each one of these blobs is. So now we can see that these are PNGs of sort of a reasonable resolution. Then if we pipe it to sort, we can start sorting by that average blob size. So the better candidates for LFS sort of float towards the top. And then if we write that out to a file and run the report on large objects command, which also comes with RepoFactor, it'll actually give us some output saying, hey, these are the paths to each one of these files. And we can use this as input to our BFG command to start converting our repository over to a much, much smaller version of our repository with LFS enabled. So once we've got converted over to LFS, we simply need to find a place to store our repository. If you're using Bitbucket Server, you can enable LFS by checking a checkbox in your repository settings. I believe in GitHub it's fairly similar. And then once you're there, in Bitbucket at least, we automatically read through to your backing LFS store. So we don't display those pointer files in the UI either. Instead, you'll just see those actual large contents in diffs and pull requests and all of that good stuff. So that's how you can convert over to LFS. Now I want to talk a little bit about how teams can use LFS to collaborate on the same software project together. Now, the most important thing you need to know about using LFS in a team size greater than 1 is you have to be very, very careful about binary merge conflicts. So no one enjoys resolving merge conflicts, but fortunately Git has a very, very sophisticated merging algorithm that means that you really only run into conflicts where people have changed exactly the same line on different files. Because it's very good at resolving those for you automatically. Now, unfortunately, with a binary merge conflict, Git has no way to semantically resolve those conflicts when two different people have made changes to the same file. So you can run into these really awkward situations where you've spent all day making changes to a particular large file, and then you find out that someone else has been working on that same file on some other branch. And you run into this horrific situation where you both rush to commit and push as quickly as possible so you don't have to be the person to resolve that merge conflict manually by reapplying your changes on top of theirs. Now, version control systems have actually had a solution to binary merge conflicts and all sorts of merge conflicts through locking for quite a long time. Now, locking is kind of a dirty word when it comes to distributed version control, because one of the really powerful things about Git is you have your own copy of the repository where you can do whatever you want to your source code and then resolve those changes later on. However, binary merge conflicts are so painful that we've decided to implement locking in LFS in order to address this problem. Now, there's a proposal out for implementing locking, and it's actually in the process of being implemented on the master branch of the LFS project right now. It hasn't actually shipped in a version of LFS yet, but I just want to explain how it works because it's kind of cool, and I think that they've implemented locking in quite a Git-like way. So Steve Streeting, the Atlassian who proposed it, in his proposal first talked about how not to implement locking in Git. And I think this is important because the naive way of doing locking is kind of breaks one of the most important features of Git. Now you can imagine it would be very easy to force developers to serialize all changes to a particular large file on one branch. So for example, a developer wanting to modify our picture of an elephant might acquire a lock on the master branch, make their changes, and then release that lock once they're ready for other developers to make those changes. Now this would work, and it would prevent binary merge conflicts, but it would also break branching. As a developer, you kind of want to be able to work in an isolated environment on a branch before merging your changes back to master. And in this situation, you'd be prevented from making any changes to this file unless you're sitting on the master branch, which is terrible and kind of anti-DVCS. So instead, Steve proposed a multi-branch model for implementing locking. Now, the way the multi-branch model works is pretty simple. Basically, you can acquire a lock on any file in the repository or on any branch, provided that you have the latest version of that file and that no one else has acquired a lock on it. Now, I'll show you how that, so it's kind of simple rules, but how that actually pans out in practice is kind of cool. So imagine a developer, again, wants to make a change on the master branch. They can acquire a lock, make their change, and then release the lock. Now at this point, if a developer on the, say, the feature 1 branch also wanted to make a change, if they tried to acquire a lock, that would fail because they're trying to lock a previous version of that file when a newer version exists on a separate branch. Now rather than forcing them to check out that branch, we actually allow them to rebase or merge that branch into their feature branch to get the latest version of that file. And then they can acquire a lock and make their changes. But what's really nice about the way this locking has been proposed is you don't actually have to have a straight line of ancestry from your the tip of your branch commit and then the commit where it was last changed. The locking proposal that's out there is actually saying you can, say we are on the feature 0 branch, you can actually check out just that individual file on top of your branch or cherry pick that commit onto your branch or even just copy the contents of that file and put it into your work tree. As long as you have exactly the same contents as the latest version of that file, done again via a SHA-256 hash of its contents, then you're allowed to modify it. So if I check out just that file on top of my tip commit on my branch, I can acquire a lock and make those changes. So it's quite an elegant way of serializing changes to the same commit across multiple branches. So it's actually completely orthogonal to Git's branching structure. But it's still kind of a nice way of preventing binary merge conflicts without really overly restricting developers. Now, as I mentioned, this work is still in flight, so these commands are still kind of provisional. But probably how it's going to work is we'll have a lock command where you lock a particular path in your repo, and this will tell the server that you've acquired a lock on that particular path and syndicate that out to the other clients. Then you can run Git LFS unlock to unlock that afterwards. And we're also going to have the ability to force an unlock. So if a developer locks a file and then leaves the company, you can still unlock that. So it's really a guidance rather than like a hard and fast rule about the fact that you cannot modify this file. And then you can run the Git LFS locks command to list outstanding locks inside your repository. Now, unfortunately, as I mentioned, this work hasn't actually shipped yet. So until then, if you're planning on adopting Git LFS, the best way to avoid binary merge conflicts is just to kind of manually pass the mutex to other team members. So if there are other people who are likely to be modifying the same file as you, just tell them that you're going to be modifying it before you go and spend half a day creating a horrific binary merge conflict that someone's going to have to resolve. So mainly so far I've been talking about how an individual developer interacts with their Git LFS repository. But in some situations, you might want to pull down LFS content off other branches that other people are working on. Now, when you do a git checkout of a commit and Git LFS actually reads through to the backing LFS store, it's doing what's called an LFS fetch, which is kind of similar to a git fetch. It inflates all of those pointer files that you have locally into their LFS objects. You can also pass the -- recent flag to this command to fetch large binary content relating to recently updated branches in your repo. Now, by default, Git LFS considers a recent branch any branch that contains a commit on it that's newer than 7 days old. So you might use -- recent if, for example, you wanted to review some coworkers' changes and you just wanted to pull down all of those recent changes in one batch rather than individually checking them out and waiting for those downloads. Or for example, if you're about to jump on the plane to LinuxCon, you've got 10 hours to kill, and you want to review some code, you might run this first because you're going to be offline and you won't have access to that LFS store while you're in flight. If you like this behavior, you can set the configuration property LFS fetch recent always, and it will always retrieve this large content, which might be useful if you're working in a relatively small team or on a fairly slow-moving repository. You can also tweak some other properties of the LFS fetch recent behavior. You can change that sliding window of recency by configuring fetch recent refs days, or you can actually retrieve content for commits that aren't the heads of other branches using fetch recent commits days. Now, by default, this is set to 0 because that could get quite noisy depending on how often these files change in your repo. But I can imagine you might want to use this if you were planning on doing some history rewriting, so maybe some like rebasing or cherry picking, and you wanted to get this large content from other developers. In that case, you might want to adjust that to some other more appropriate value. You can also set the fetch recent remote refs property, which is a binary property. What this does is it actually will go off and download LFS content for every single branch that the server knows about, or every single ref rather, so branches and tags that the server knows about. This defaults to false quite sensibly because that could be a huge amount of data depending on how active your repo is. So unless you have very special circumstances, I recommend keeping that off. Once you've been working with LFS for a while, you'll notice that that LFS object cache sitting in your .git directory starts getting bigger and bigger and bigger. And by default, Git LFS won't delete those objects because you may actually want to keep those around if you want to check out earlier commits from your repo. So what you can do is run the Git LFS prune command to actually go back and clean that up. And what this does is this will actually force LFS to go back and delete objects that it thinks you don't need anymore. Specifically, it'll delete any object that is no longer recent, so using that same recency rule that we looked at before, that it also applies an offset of 3 days to that, just as like an additional little safety barrier. It will also never delete any LFS files that are currently checked out, or any LFS files that are related to a commit that hasn't been pushed to the server yet. So it does that by comparing your local versions of branches with the versions of branches on the server, and it won't delete anything that's that hasn't yet been pushed. You can also tune these properties using the prune offset days property, which will basically change that offset number from 3 to something else. And you can also set this thing called prune verify remote always, which I actually recommend turning on, because what this does is it'll actually verify with the server that the object exists on the server still before it deletes it locally. So that's kind of a really nice safety check to make sure you're not irrevocably deleting content that is no longer tracked on the server. Of course, if you do create a branch that you do actually want to delete and throw away, then you'll have to temporarily disable this in order to be able to delete those corresponding LFS objects. So that's how you can fetch more LFS content than potentially you need. You can also configure LFS to download less LFS content in certain circumstances. Now, why would you want to do this? Well, in some projects, the LFS content for a repo or for a particular commit even might be a huge amount of data. So for example, if you're working on a video game, and you're configuring like a CI build or something like that that's just running unit tests and doesn't need all of your models and textures and sound effects and all of that, gigabytes of data, then you can exclude something like your assets directory using an exclude pattern when you run Git LFS fetch. Or alternatively, if you're a specialist on a team, you might only want to download a certain class of assets from your repository. So for example, an audio engineer might want to just download the sound effects and music and things like that for the video game. And they can do that using an include pattern. Now these patterns are exactly the same as you'll find in your git ignore files in your repos, which you may already be using. They're just basically ant globs. And then you can also configure these permanently using the fetch exclude and fetch include properties. So I think that's all I've got for today, and I'm almost out of time. Maybe I can take a couple of questions. Yeah, if anyone has questions. But before we do that, if you want to learn a little bit more about the LFS project, you can check out the docs on the GitHub static site. So as I mentioned, it's a joint project between Atlassian and GitHub. The source code is also there. It's written in Go, as I mentioned, but it's also a really good example of how to extend Git. So if you want to learn about how to build filters and push hooks and all that kind of stuff, definitely check it out. It's shipped in Bitbucket Server 4.3, and Bitbucket Cloud is coming very, very soon. Product management told me not to be specific, but check next week. And so you should be able to use it for all of your repos on bitbucket.org. Thank you very much for your time.